Pedigrees. A pedigree is the kind of like a little family history that tracks the occurrence of certain traits. So it's basically it's a flow chart tracking the occurrence of a trait in a family tree. So it's kind of like drawing a family tree. Very similar. But we have some specific symbols that we use to describe things. So first I'm going to go through the different symbols that we have for drawing a pedigree. Okay? And then we'll draw a couple examples and just kind of look at them. So here's the symbols. When we draw a pedigree, we use an open box for a male, and we use a circle for a female. And these are all sort of standardized so that everybody understands what we're talking about. All right? If a female and a male get together and mate to have children, then we simply draw a line between the two. So that represents two parents. That's a mating between two parents. Okay? And of course, we're only dealing with mating. I mean, we're just talking about male-female combinations only because that's the only ones that can biologically produce offspring. It's not that there's any, specific prejudice against same-sex couples or anything like that. But in the pedigree, they wouldn't really have any offspring to speak of, right? And of course, if they had adopted children, that wouldn't matter in terms of the passing on of traits or genes because they would be different genes. So in a pedigree, it's always a male-female process. Now, when you have people who, when the box is open like this, or not colored in, it means that they're of normal phenotype, okay? When the box is colored in the pedigree, that's what we call an affected male. In other words, they're carrying, they're exhibiting the phenotype, the recessive phenotype that is whatever the condition might be or whatever the trait is. So affected is what I meant to say. It doesn't have to be a disease, it could be any trait, but these are the ones that would sort of have the trait. So that's an affected male, right? And then the colored in female would be the same thing, an affected female. Then, of course, we have to figure out how to deal with children. So, children are usually drawn like this. The offspring, if you have a male and a female who have mated together, then typically what we do is we draw a line down and out like this, and we put the children like that. So maybe there's a girl and a boy and a boy and a girl. And we typically put them in order of oldest to youngest. Not necessarily, it doesn't have to be that way, but typically the oldest goes on the left, and then they go down towards the youngest. But again, that's not critical. Now, sometimes you can have interesting situations. Like, what if you had twins? Twins are very genetically unique, right? Well, they have the same genetic makeup if they are identical twins. So when we do twins, we have some little twins. So if they're identical twins, right, then what we do is we take the mom and the dad, put them together, draw our line like this. Now maybe they had an older child who was a female, and then they had two identical twins. Well, if they're identical, they'd have to both be the same. So let's say they were both girls. If they're twin girls and they're identical, we draw the line like that. So it's like a little triangle instead of just a single line. And you'll notice that the line between the two, I'll put that line, I'm talking about this line right here in red, that's joining them. That means identical. The two angled lines that I'm drawing in green mean twins. Okay, and maybe they had another older daughter or something, younger daughter, whatever. So that right here indicates how we deal with identical twins in a pedigree. Now, what about if they're not? What if they're fraternal twins? Fraternal twins are a little bit different. So you have a mom and a dad and mom, and we have some babies here. And so maybe they have a set of twins. We would draw them like this. They still have the two. So there's a boy and a girl, which they can be. Fraternal twins are not genetically identical, but it does indicate that they are born as twins at the same time. And then maybe they had another child and another child, big family of 4, who knows. So the thing that's different is they don't have the joining red line between them. So the angled little top of the triangle, which I'll highlight in green right here, indicates twins, but it's fraternal because you'll notice there's nothing here connecting them. That's the difference. The red line here is what indicates the identical part for the twins. So that's how we deal with twins. In some cases, in a pedigree, we might not know the sex of someone. It's possible. And if you don't know the sex of someone, then you can't draw it as a square or a circle. You draw it as a diamond shape. Unknown sex. And this would often happen. I mean, clearly the people that are close to you, you would know, but if you're going back in a family tree many generations, there might be, this person you know of whose name was Pat. Well, it could be a boy, it could be a girl. We don't have a birth certificate. We're not sure. It's kind of like, as you go further back, records become less and less accurate. So there are times where we have an unknown sex and we're not sure. Okay. So we could do an interesting sort of pedigree for people who have something that runs in their family. So let's just kind of do an example. The example we'll do is something called let's do Huntington's disease. As an example, Huntington's disease. Okay, Huntington's disease is a serious disease that causes the brain to sort of degrade over time. It takes a while, maybe 15, 20 years, and so you end up with all kinds of issues, and it's eventually lethal. So here's an example of a pedigree. Okay, let's say in this particular pedigree there was a female married to this male, and let's say that they both had Huntington's disease. Let's just say what would happen. All right, so now, what's interesting about this disease is it's dominant. So if you write that down on the side, it's a dominant thing. So that means that all you need is one allele to have this condition. So here's two parents, both of them who have the condition, but then they decide to have children. And when they do have children, they have 4 children. So we go over here like this, and we draw their 4 children. 1, 2, 3, 4. Out of those 4 children, they have this male who does have Huntington's disease. They have a girl who also has Huntington's disease. Then they have two more girls who do not have Huntington's disease. Okay, so that's the sort of the first offspring generation. Now, perhaps the female on the left side here, no, let's do the male first. The male on the left side marries or mates with a female who is normal. She does not have Huntington's disease. Then they have their own children, so we draw their children like this, and there's going to be 3 of them. And they produce a male who has the disease, a female who has the disease, and they have a child. Oops, sorry. I'm just copying this out of the book so I don't mess it up. So we'll just copy this. This is a female who is normal. And then over here, we have, on this side, this particular female marries a normal male, and they produce 3 normal children, or non-affected. We use the word normal. It's not necessarily the best word to use, so affected or non-affected, I suppose, is a little more politically correct. But the problem is that genetics has been going for many, many decades, and so you'll hear words like that, and don't be upset about it. So here's the pedigree, 3 generations of this family. Now, automatically, because of this pedigree, we can determine some things, right? If we look at the possibilities, because we know it's a dominant gene. We know something now about the genotype of those parents. Because if it was a dominant gene, and they had both dominant alleles, right? If we take a look at the mother's genotype, and if she had the genotype of, let's call it capital H for Huntington's, and capital H, which would make her have the disease. And if the male also had that same genotype, well, it's clear to see if you did Punnett squares, you would have only capital H's, and all of the children would have to carry the dominant capital H, which means all of the children would have to have Huntington's, right? But clearly they don't, because here are 2 females who came out normal. So what that means is that there has to be a way for the small h recessive condition to occur. And so that means if we change this to a small h and imagine the Punnett square. Now, if you can't imagine it in your head, you can just do the Punnett square cross. Would you get any normal children in that case? You wouldn't, because the female is still donating a capital H, right? The dominant gene, no matter what, which will mask that allele. So we now know that the only way that it's possible to get at least some children who are not carrying this or not exhibiting this is to have 2 heterozygous individuals. They both have the disease because they carry the dominant H, but there's a chance those 2 small h's could get together, right? So in this child, this daughter, and this daughter, it's clear that that's what happened, and they do not carry or have Huntington's disease. Whereas for these 2 children over here, obviously it was either the 2 capital H's or a capital and a small, the dominant and recessive, that got together. So see, we can use the pedigree to figure out genotypes of certain people in certain conditions. Okay? Then we can go down below here. Now, what you can't do, and this is the thing, because humans only have a few children, you can't do a Punnett square and say, oh, the Punnett square says 1/3 will have the situation, and if they have 3 kids, you can color one in and say, oh yeah, the 1 out of 3. Remember, those Punnett squares are probabilities, right? And they're only really useful if you have hundreds of offspring to use to get those probabilities. So we can't use the Punnett square with only 3 children to prove what the children must be. But we can use the Punnett squares to sort of work backwards, and we know what the children phenotypes are. So that's what makes them useful. Obviously, if we look at this side of the table, right here, it's safe to say that with two normal individuals, the only way that you can be normal with this Huntington's disease is if you are both homozygous recessive. And if that's the case, there is no capital H. So the rest of this family tree, the rest of this pedigree, and wherever it continues, as long as the people who are mating into the tree don't carry it, we can safely say that this line of the tree does not have Huntington's, right? It will not be there. However, the other line of the tree over here, you can see still has affected individuals in it. And so we can continue here and imagine what might be the case. So when you look at this, you know that this female right here is recessive, homozygous recessive. But we don't know what this one is, but we can guess. Because it has to be either two capital H's or a capital and a small, right, in order to be colored in. But look at this child. They did produce a child who was not affected. That tells us that this allele right here had to somehow be in the mix. Now, it could have come from here, but look at this. If that was the father, then he would always give a capital H, and every child would have the capital H. So the fact that this particular girl right here is not affected means that the mother must be this. We know that because she's perfectly healthy. But look at this. He must have carried this. So now we can identify his genotype, right? We can use this sort of backwards puzzle-solving strategy to determine what the actual genotypes were of the people. And that's what the pedigree is for. And so there will be questions where you will have to look at a certain pedigree and try to figure out what the genotypes might have been for a particular individual in the pedigree. Okay, any questions about how that works? It's pretty straightforward. Okay, we'll stop this here.